A very quick intro. We're going to have Fadel Adib today. He's the Doherty Chair of at MIT and an Associate Professor at the Media Lab and also the Electrical Engineering and Computer Science. He's the founding director of the Signal Kinetics Group, which invents wireless and sensor technologies for networking, health monitoring, robotics, and ocean IoT. He has a number of awards. I think he has them all. And so, like very promising scientist. And not just this, I was mentioning earlier that he has this cool image because he was with President Obama presenting top technology a few years ago in the White House. So we're excited to have today Fadel Adib. He's not going to have a clinical collaborator today with him. He's going to do the talk by himself. And Fadel, if it's okay for you, sometimes there's interruptions, people jumping in, asking questions. So we'll try to moderate, but if I see any question on the chat, I'll try to help. Otherwise, feel free to run it. And sometimes we leave just a few minutes, 5-10 minutes at the end of the session. The stage is yours. Thank you very much, Fadel.
Great. Thank you very much for your introduction. Start by sharing my screen. Can you see my screen well?
Beautiful.
Wonderful. Great. Thanks, everyone, for being here. My name is Fadel Adib. I'm a faculty here at MIT in EECS and in the Media Lab. And today I want to tell you our research project on wireless seismocardiography, which is funded by Jameel Clinic. Now, when we started this project, we were motivated by a simple question, which is, can we capture a person's heart recordings without any contact with their body? So for example, let's say I'm sitting here in my office, there is a device that sits on my desk, and this device, even without it being in contact with my body, can extract my heart recordings. Now, why do we want to do that? Well, cardiovascular diseases are the #1 cause of death in the world. Even over the past 2 years during the pandemic, more people died of heart diseases than from COVID-19. In the United States alone, 1 person dies every 36 seconds from heart disease. Yet many medical studies have shown that if you can diagnose heart disease early through continuous monitoring, then you can lower fatality rates by 30 to 70%, depending on the type of the heart disease. So why aren't we all continuously monitoring our hearts and monitoring, capturing heart recordings? Well, there are many different approaches for heart recordings today, and all of them can recover rich recordings. All of those that can recover rich recordings have one thing in common, which is that they all require contact with the human body, and many of them are quite cumbersome. I'm sure some of you might be wondering, oh, don't smartwatches, for example, like the Apple Watch, also get heart rate? And the answer is yes, but heart rate alone is not enough to monitor and diagnose a lot of the cardiovascular diseases. Instead, you need methods that not just get the average heart rate, for example, of 70 beats per minute or 100 beats per minute. You want to be able to capture the entire heart recording, for example, like what you typically get using an ECG or an SCG, which is a sensor that goes on the body and measures the mechanical movement of the human heart. And today, so if you want to capture these today, you need to rely on these contact-based modalities and fairly cumbersome devices. And even if you and I are willing to wear them, they're not suitable for certain sections of the population. So for example, high-risk populations, sometimes babies or elderly, they're either not comfortable wearing them or they have sensitive skin. In scenarios where you want to be able to monitor infectious disease patients, for example, today, if you want to be able to monitor COVID-19, sometimes you have people and trying to take the thermometer from a distance to take someone's temperature. And it would be great if you can also monitor capture someone's cardiovascular recordings also from a distance. And also, there's many scenarios where you simply can't do contact-based cardiovascular monitoring, for example, for burn patients or patients who have very sensitive skin. And so because existing approaches are either cumbersome or either not accurate, what I want to tell you about today is our journey on how we could extract heart recordings without any contact with the human body. And the way we do this is by relying on wireless reflections. So let me tell you how our technologies work. We have a device. The device sends a wireless reflection, which reflects off the human's body and comes back. And the device uses these reflections in order to capture tiny vibrations of the chest that correspond to the heart movements. So whenever the heart contracts and relaxes, the captured reflections will exhibit peaks and valleys. In fact, our system can even capture microcardiac events, which correspond to the opening and closing of heart valves that regulate the blood flow between heart chambers. So for example, if we zoom in on these signals, we can see that our system can, for example, detect the aortic valve closing, the isovolumetric contraction, the aortic valve opening, the mitral valve opening and closing, and so on. And the reason is that every time any of these valves opens and closes, it causes a very tiny vibration that travels through the human body and which can actually be monitored from a distance using our device. Medically, what we're able to do is we're able to extract what is called the seismocardiogram, which is a recording of the human's heart's mechanical or seismic movements. And these microcardiac events and their timings have been used over the past 2 decades to diagnose various cardiovascular conditions, but using methods that where you need to put a sensor on the person's body. And we wanted to be able to do this without putting any sensor on the body. And in this talk, I want to tell you how we do this, how we can use wireless reflections to enable long-term, non-contact cardiovascular monitoring. And first, I'm going to be telling you about a system that is called RF-SCG, which can perform contactless or non-contact seismocardiography, how we can extract these time domain heart recordings, and how we can also automatically label different microcardiac events like the ones that I told you about. Then I will tell you about how over the past few months, we've been building on the fundamental capability of RF-SCG to move from diagnosis toward prevention. So, for example, one of the key factors that is known to increase the risk of heart diseases is stress, especially chronic stress. So in the second part of my talk, I will tell you about a system called WiStress and how it enables us to capture cardiovascular recordings in a motion robust way, and how it goes beyond cardiovascular recording in order to measure a person's stress levels. And toward the end of the talk, I will also share with you some of our other research that my group has been doing in wireless sensing for other health applications, and highlight how the fundamental technologies that we've been building have applications that extend even beyond health. But before I start telling you about our research, let me first give you a little bit of background on this line of work and the historical context in which led us to this. So the type of work that we do on non-contact human monitoring using wireless reflections can probably be dated back to the development of radar in the early to mid 20th century, where researchers realized that you can actually use wireless signals that are traveling in the environment in order for you to detect and track objects. And radar progressed a lot in the 20th century. In the early 2000s, there was military research on using radars to detect people through walls. The basic idea was to take these radars, instead of pointing them, for example, to space to track airplanes, you point them through the wall. And these large and expensive radars were used to be able to detect people on the other side of the wall. So they were expensive, they were large, and they were mainly limited to detection, but that was the progression of where we were in the early 2000s. Then about 10 years ago here at MIT, we started looking at and experimenting whether we can use low-cost and low-power Wi-Fi devices to see through walls and track people's movements and gestures. And our idea was similar to radar, where you use these wireless signals that are traveling, but instead of building expensive and bulky radars, we wanted to rely on off-the-shelf Wi-Fi devices. And over the past decade, this research on Wi-Fi based and sensing evolved into a field that is called today wireless sensing, where we and other researchers around the world have demonstrated the ability to detect people, to get their locations, their gestures, their movements, and even how we can extract people's breathing and heart rates. And so this is what led us to all the stage up until before we started working on the project of non-contact cardiovascular monitoring. And what we were specifically curious to in this project is whether we can also use these low power wireless signals to not just get people's average heart rate, for example, 70 beats per minute versus 100 beats per minute, to being able to capture microcardiac events. So knowing when heart valves open and close, because these and their timings are correlated with different cardiovascular diseases. And this is what motivated us to start to work on this project. And so in the first part of my talk, I will be telling you about RF-SCG, which is the first system that allows us to capture and fully reconstruct seismocardiogram waveforms, which are SCG signals, without requiring any contact with the human body. And this technology is based on a novel and hybrid pipeline where we combine signal processing and deep learning through a series of learnable spatiotemporal filter functions. And I will also tell you how we evaluated this on, empirically evaluated it in user trials on 40,000 heartbeats and demonstrated how we can accurately time microcardiac events with over 99% accuracy. Now, the architecture of our system, which is RF-SCG, consists of three main stages. The first one is the stage where you get these wireless reflections and you try to zoom in on the reflections that are coming from the human heart. Once we zoom in on the reflections of the human heart, we capture these wireless reflections and then we transform them into SCG waveforms. And finally, once we have SCG or seismocardiogram waveforms, we developed a module that automatically labels them in order for it to detect, label, and time microcardiac events. And I will start by going through each of these modules or each of these steps one by one, and starting with the 4D cardiac beamformer. Now, remember what I said, that our device uses wireless reflections in order to obtain heart recordings. But what happens is if you have a device and you send wireless signals, you actually get reflections from everything in the environment. So the signal is not just going to reflect off my body, it's going to reflect off tables and chairs and the wall. And even from my body, it's not just going to reflect from my heart, it's also going to reflect from different body parts. So the first question that we had is, from all of these reflections in the environment, how can we isolate and zoom in on the reflection that is coming from the person's heart in order for us to start studying this reflection and capturing the minute vibrations that are coming from the microcardiac events? So to do this, what we want to do, our first idea was to do beamforming. Now, beamforming is this concept from wireless communications, where what you do is you're able to focus your beam in a specific direction. And what we wanted to do is to be able to form or focus a beam on the person's heart. Now, of course, the problem that we had is if you have a device and you have someone in the environment, you don't even know where the person is sitting or where the reflection from the heart is. So the very first step for us to do is to scan the environment and try to look for the person's reflection. So when you have a beam, you're able to actually shift it in the environment and try to search for the person's heart. And in standard beamforming, for example, if you look at trying to find airplanes, sometimes what you're usually doing is you're looking for the strongest reflector. But in our scenario, is the heart the strongest reflector? It's usually not the strongest reflector in the environment. It's not even the strongest reflector in the person's body. Usually more reflections come, for example, from the person's belly or from the person's head. Is it the fastest moving object? The heart is not moving very fast. It's contracting and relaxing, but it's not moving fast. And it's also not the smallest movement. So it's neither the fastest movement, nor the strongest movement, nor the smallest movement. And especially when it comes to wireless, you can't simply say what is the smallest movement, because then you start wondering whether something is noise or whether it is an actual movement. So in order for us to find and zoom in on the heart's reflection, our idea was to introduce a 4D cardiac beamformer. And the core idea under the 4D cardiac beamformer is that we're going to look in 3D space, but also search for periodicity in space. And the high level idea there is, because the human heart's pumps or functions in a relatively periodic movement, we're going to try to look for this periodicity in the environment and try to search for it as we search the space to zoom in on the heart's reflection. So the way this works is that our beamformer starts by searching in 3D space and in frequency in order to look for the heartbeat repetitions. So let us take an example. Let's say that we divide all of space into voxels. So for example, we take this XYZ voxel in space, and we zoom in on it, so we beamform to it, and then we're able to extract the vibrations over time, as you can see here. This is the time domain signal that comes from the specific voxel in 3D space. So let us take now another voxel. This one is on the person's body, and we also extract the time domain signal, and so on and so forth. So by zooming into every 3D voxel space, we can then extract the time domain signal from each of them. And the question then becomes, which of these corresponds to the person's, to the one that comes back from the person's heart? So here's an idea. If I know what the person's heart rate is, then the problem becomes much easier, because if I know the heart rate, then I know the frequency at which the heart is beating, and I can search in each of these for this frequency. If I search for each of these for the frequency, then, for example, I can then project on that frequency and know which is the one that has the most dominant frequency that corresponds to the heart. So for example, in this example that I'm showing over here, if you look at the second signal, this one, it turns out that this one has a periodicity that corresponds to the person's heartbeat. And in fact, if you look at, it looks like it has a seismocardiogram, which has like multiple different reflections with the variations that we usually would expect from the heart. And so one assumption that I made here is that I already know what the heart rate is, and by searching for the heart rate among these, then I'm able to look for them. But in reality, we have an idea of what the heart's template looks like, and so we can do this search in 4D space. So formally, the way we formalize this is using a 4D projection on each 4D voxel in space. And as I mentioned, the way we do this is we take an FFT, or a projection in the frequency domain, and then we also do a projection in the X and Y and Z domain for every voxel in 4D space. And once we're able to project all of 4D space and get the power, the frequency time space power in each of these, then we're able to take the maximum, and the maximum usually corresponds to the person's, to the location in 4D space where the person's heart reflection is. So just taking a step back, what we did here is we searched 3D space, then we searched in time, but we transformed time to frequency. And by doing so, we were able to search for the periodicity. And because we know the heartbeat has a certain type of periodicity, we were able to find it, zoom in on it, and then we're able to iteratively zoom on it and find the person's reflection.
Okay, so you know, how far can be? How far can you be to really be proficient?
We're able to operate at up to about 12 feet, so about 3 to 4 meters. It is able to work robustly.
Okay, thank you.
Yeah, thank you. Using this 4D cardiac beamformer, you can zoom in on the heart's reflections, and now we're able to isolate the reflections from the heart from all of the other reflections in the environment. And this is great. So for example, here I'm showing an actual time domain signal that are for the cardiac beamformer obtains. And in fact, if you compare it to an SCG waveform, so what we did here is that we also put on the person's body an accelerometer, and we extracted the time domain signal. And if you compare it to the time domain SCG signal that we got from an on-body accelerometer, you realize that they look very similar. In fact, you see that there's 2 regions, for example, that have peaks, which actually correspond to the systolic and the diastolic part of the heartbeat. But if you actually zoom in more on these, you realize that the peaks and valleys in these signals are not very well aligned. So in fact, the correlation between these 2 signals is usually between 0.4 and 0.6. And this relatively low correlation is pretty bad if what you want to do is to be able to time microcardiac events, because they're going to be shifted a little bit from each other. So even though both the on-body accelerometer and the wireless reflections were capturing the heart's mechanical activity, they are inherently different modalities. And this is why, actually, when you try to correlate them with each other, even if they're perfectly synchronized, they don't end up being very well correlated. And this is problematic if what you want to do is time microcardiac events. And so what we wanted to do fundamentally is to figure out a transformation between the radio signals and the SCG waveforms. And as we started looking at this problem, we knew that this translation should be possible because they're both based on the same mechanical activity. Both of them are due to the mechanical vibrations that are on the person's body. Now, when we started looking at this, the simplest approach was to implement some form of filter, like a finite impulse response filter that tries to transform the radio signal to the SCG signal. But as we experimented with this idea, we realized that linear filters alone did not give us very good accuracy. And so we needed a more generalized transformation that includes both linear and nonlinear components. And once you have linear and nonlinear components, in fact, we stacked multiple different layers on top of each other, and we ended up with a standard multi-layer convolutional neural network. So by implementing a simple, I think, 4 to 5 layer deep neural network, we're able to increase our correlations from 0.4 to 0.5 to around 0.8 to 0.9, which is much higher. And now that we have this much higher correlation, we started thinking as to whether we can now time different microcardiac events. So, so far, I've told you how we can zoom in on the person's heartbeat in the environment and isolate it. And if there's multiple people, you can actually isolate each of their heartbeats. And once you isolate it, I also told you how we can transform this wireless reflection into an SCG waveform. Now that we have a translated waveform, what we wanted to do is to be able to time the microcardiac events and do automatic labeling. And to do this, automatic labeling is a well-developed field that has seen significant advances, for example, in computer vision over the past few years. So one of the areas where it's seen significant advances is in image segmentation, where you have an image and you're trying to segment this image into different regions. Now, instead of 2D, what we actually wanted to do is to label a 1D signal in the time domain. So we adapted a standard segmentation network that is based on the UNet architecture to our problem domain. And let me tell you at a high level what we did. So our architecture is trained to learn filters for 5 different microcardiac events, as you can see here. And so when it learns these filters, it can automatically detect and label the microcardiac events that correspond to the mechanical activities, which are, as I mentioned, the opening and closing of heart valves and the contraction of heart chambers. And so once we train this architecture, we're able to learn each of these different filters and automatically time the different microcardiac events. Now, in our paper, we describe the details of exactly how we implemented this architecture and each of the layers. So I want to tell you a little bit about how we implemented and evaluated our system. Over here, you can see the board that we use. It is the same as the board in my hand. These are off-the-shelf boards that you could actually buy on the market today. They have a 77 gigahertz radar, which has multiple antennas on board. All of these antennas allow you to do 3D beamforming, so in 2D and in range. And for ground truth, the person wore an accelerometer on their body in order for us to capture the vibrations that happen on the person's chest. Now, the on-body accelerometer was only used in training and in ground truth, and we didn't use it when we were actually evaluating our device. We collected 40,000 heartbeats from more than 20 subjects. We also implemented some outlier rejection, and we did a number of data augmentation for the RF-to-SCG translator so that we can expand the number of measurements that we're using and increase the robustness. So first, I want to show you the reconstruction accuracy of our system. So what I'm going to do is plot the correlation on the y-axis between the ground truth SCG obtained from the on-body accelerometer and the contactless measurement that we're getting from the reflections after we did the RF-to-SCG translation. And I will do this for each of our 21 different subjects. So first, I want to show you the output of the 4D cardiac beamformer. As you can see, the correlation from the 4D cardiac beamformer was somewhere between 0.4 and 0.6. And now I want to show you the output. Here you see in blue the output that we got from when you combine both the beamformer and the translator, and you can see that we're able to get a significant boost from 0.4 to 0.6 to around 0.8 to 0.9 in being able to reconstruct the SCG waveform. And what this shows is that you're able to, for the first time, extract the entire SCG waveform from wireless reflections. Next, I want to show you, remember that another goal that we wanted to do is to be able to automatically time the different microcardiac events. And remember that the different key peaks that we got and the values in the waveform correspond to, for example, the opening and closing of different valves and the contraction of heart chambers. So here, what I'm going to show now is I'm going to plot the CDF as a function of the accuracy on the x-axis. And these are the results. And of course, being in the top left is better. So here are the results that we got. As you can see, interestingly, 3 of these microcardiac events have a median accuracy that is higher than 99.5%. And all of these correspond to the systolic component of the cardiac cycle, which is when the heart contracts most. So if you see for these three peaks, the accuracy is even higher from the other 2 peaks for the diastolic. And actually, when you try to hear the heart, if you try to hear the heart's recording, you actually do always hear a louder beat than a weaker beat. And the reason is that in the systolic, the beat is higher, and that's also why the SNR is higher. And when the SNR is higher, you're able to extract it with even higher accuracy. But most importantly, what this result shows is that even for all 5 microcardiac events, we're able to extract them with more than 98% accuracy.
Question?
And so we were pretty excited about this result. And we started taking our device and started testing it. For example, I started installing the device in my office, and I wanted to see if I can continuously monitor my microcardiac events over an extended period of time. And remember that we had an accuracy that was higher than 90%. But when we started doing some of these longitudinal studies, we realized that the accuracy quickly dropped from more than 95% to about 60%. So there's a question from Sahar.
Yes, hi Fadel. Great talk so far.
Thank you.
I wanted to quickly ask so how are you measuring this accuracy? What are you measuring it against? Like the real heartbeat?
This is a great question. So when we talk about the accuracy, we're measuring it as a function. So this is the error with respect to the length of the heartbeat. So 100%, so an error, for example, of 1% means it is about less than like 10 milliseconds. So in our paper, we also report the exact error as a function of milliseconds. What you care about is how much these different peaks and valleys are shifted from their ground truth. So we take this shift and we divide it by the length of the heartbeats. So
great, thank you.
Thank you. So when we started doing these long-term monitoring tests, we realized that the accuracy dropped. And the reason is the accuracy still works very well if someone is sitting perfectly static. So for example, if I sit and I don't move for a couple of minutes at all, then we are able to get this very high accuracy. But when you stop restricting the people's movements, and even for those of you who are just like sitting and watching, you might be typing, you might be moving a little bit in your chair. And this alone is quite bad, and it caused the accuracy to decrease. So we started thinking whether we can enable motion robust heartbeat extraction so that we don't restrict people's movements, and yet we're still able to maintain this high accuracy. The second thing that we were thinking about is whether we can move from monitoring to being able to enable prevention. So for example, what I mentioned earlier in the talk is stress was one of the was a key factor that increases the risk of cardiovascular diseases. And we started thinking whether you can monitor a person's stress level using the vital signs that you're able to capture and use these as an intervention mechanism, for example, to tell people to take breaks, or if they need to attend for their mental or emotional well-being so that they avoid running into cardiovascular issues. And so this leads me to the second part of my talk, where I want to move from talking about cardiovascular recordings to being able to monitor people's stress levels. And as I mentioned, the goal here was in order for us to avoid scenarios where today, prolonged stress or chronic stress, it impacts our brain, it reduces our productivity, it accelerates aging at the cellular level, it leads to many cardiovascular diseases. And because of this, actually, over the past few years, we've seen a number of stress monitoring solutions to support mental health and well-being intervention. For example, by monitoring stress, doctors can provide better medications for patients with anxiety or depression. Also, even if I can monitor my own stress, then I would want to know when I need to take a break or meditate or go for a walk. The problem is that today's stress monitoring solutions are quite obtrusive. So the gold standard for stress monitoring is a cortisol test. It requires extracting saliva samples and testing for the cortisol hormone, which is correlated with stress. But it's pretty inconvenient to get a saliva sample every 15 minutes. Now, another approach is to ask people to fill in questionnaires, which is also pretty annoying. And research has shown that the vast majority of users abandon filling in questionnaires after a few days or weeks. And so this makes it difficult to use these approaches for long-term stress monitoring. So to address these, over the past few years, there's been interest in using wearables to monitor stress. And for example, by tracking breathing and by tracking heart rate variability, because research in the effective computing community has shown that these biometrics are correlated with people's stress levels. The problem with existing wearables is that they trade off accuracy for comfort. So for example, chest straps can monitor breathing and can monitor heart rate variability with very high accuracy, but they are quite uncomfortable for people to wear them on a regular basis. On the other hand, wristbands can track heart rate, and they are more comfortable, but they are less accurate in being able to extract these stress-related biometrics. And because we're able to monitor breathing and heart rate from a distance and even individual heartbeats, this got us thinking as to whether we can monitor stress using wireless signals in a contactless, unobtrusive, and fully automated way. And so what I want to tell you about next is how we build this system called WiStress that allows us to do contactless stress monitoring. And the way it works is that it transmits a wireless signal, which reflects off the person's body and comes back. And from these wireless signals, it is able to extract people's movements, it's able to extract their breathing, and it's able to extract their heartbeats. And all of these are stress-related features. And once we're able to robustly extract each of these from wireless signals, then we can build on prior work in the effective computing community and feed them into machine learning models that are able to infer people's stress levels. So for example, you can tell if a person's stress is high, medium, or low, and there's standardized ways of measuring stress. So let me start by showing you a demo of our system working in practice. So over here, again, it's the same sensor that we used before. It is on the person's desk, and it has antennas on the board. It transmits a wireless signal, and it locates a nearby user. So over here, as the user walks around and sits down, you're able to see them moving around. So for example, just repeating this, in the bottom left, you see the output screen of the device in tracking the person's 2D movements. So the background is in navy blue. This is in the form of a heat map. This is 2D space. The background is in navy blue, and the person's location is shown as this yellow dot. So as the person moved around, you saw that the yellow dot moved, and you were able to zoom in on the person's location on the chair. So this is the same idea of mapping 3D space, but we're just projecting it on 2D. And once the person sits down, you start being able to monitor, for example, different stress-related features. So we're able to detect when the person's leg is shaking, we're able to monitor their breathing, and we're also able to extract their heartbeats using this, this device. And so one thing here that is quite interesting is sometimes I get a question as to why you want to monitor movements. And the reason is it turns out that movements are also related to stress levels. So for example, when people are anxious, they're usually shaking their leg like the subject was shaking their legs. And as I will show later on in the results, by capturing and incorporating motion-related features, we're able to achieve higher accuracy than if we were to just use the vital signs. So one of the key challenges that I mentioned even leading into this is that robustly extracting heartbeats despite movements from wireless reflections is very hard. And yet being able to capture heart rate variability is known to correlate with people's stress levels. So it is very important for us to be able to capture heart rate variability with good accuracy in order for us to capture people's stress levels. So for example, this is a typical wireless signal that we get. This is similar to the signal that we got before, but instead of requiring the user to remain perfectly static, we did not ask the user to remain static. So you can see that it has a weak amplitude and it's also contaminated by noise sources. So you can see, for example, over here, there's a little bit of interference. Maybe someone was moving, maybe someone else was moving in the environment, and that contaminated the signal. And what we wanted to do is two things. The first thing that we wanted to do is to be able to detect and ignore the distortions so that we eliminate these distortions and eliminate their impact on our signal. And the second thing that we wanted to do is to be able to measure the length of individual heartbeats, which is called the heart rate variability, because the heart rate variability is a very important stress feature. So the question became, how do we automatically detect and eliminate these in a robust and generalizable way? And to do this, what we did is we leveraged a concept that is which is called self-similarity. And the high-level idea here is that what we wanted to do is to use the local similarity. Because the heartbeat repeats, then there's local similarities over here, for example, over here, over here. And we wanted to be able to use them in order for us to identify regions where the heartbeats exist and where there is little movement. And from these extract the individual heartbeats that are uncontaminated. And over the past couple of years, there's been work on what is called the self-similarity, leveraging the self-similarity matrix in the machine learning community. And I want to tell you now how we construct the self-similarity matrix for SCG signals and use it to robustly extract the heartbeats. So let us start with a simple and clean signal, a time domain SCG signal, similar to the one you see here. So this is similar to the signal that we were getting before. Now, to construct our matrix, we want to provide it with two copies of this signal, of the reflected wireless signal. Here, one is horizontal and one is vertical. Now, what I want to do is to compute the similarity between different segments of the signal. So let us zoom in to see how we're going to do this. What we're going to do is we're going to take slices of these signals in time and correlate them with each other. So for example, I'm going to take the first segment here in the horizontal, the first segment in the vertical projection, and then I'm going to try to compute the correlation between them. So because these are the exact same segment, then they're going to be highly correlated. Then I'm going to slide my window and do a second correlation between another segment and the first segment. So here, these signals don't look as similar, so the correlation is going to be low. And I'm going to keep repeating these for different portions of the segment. As you can see here, the correlation is less. But then again, the correlation starts increasing again because the heartbeat repeats. Okay, so the high-level idea is I'm going to take different, in practice, overlapping regions, correlate them with respect to each other. And once I do this shifted correlation, then I'm able to detect when the signals are highly correlated or lowly correlated. Now, at a high level, I described it as a check mark, which is correlated as an X as uncorrelated. But in practice, you can actually compute the exact correlation. And from it, you can compute a correlation or self-similarity matrix. And the self-similarity matrix starts being a feature map that has the heart rate variability. So for example, this was the grid map that we got for a full static user. And as you can see very well, it's very easy to segment it, and you're able to capture the individual heartbeats from these segmentations. Now, let me show you what happens for another user who's also sitting at their desk. They're relatively static, but they're not perfectly static. So this subject was moving around a bit. And for this non-static user, for example, you can see over here, they were relatively static, then maybe they moved their hand, and then they put it somewhere and they got static again. And this is the matrix that we get. You can see this one is much noisier than the one that we were getting before. Of course, you have the diagonal, which is the same because this is the self-correlation. But what is really nice about this matrix is that you can actually see the regions where there is repetition and it becomes much clearer and way more robust. So even as a human, I can now see that, oh, this region that is in the middle, I probably want to eliminate it. And these regions that are on the side are the ones that have repetitions. Okay, so taking a step back, what we're going to do is we're going to use the self-similarity in order for us to compute the self-similarity matrix. And once we have a self-similarity matrix, now we can apply standard 2D CNN in order for us to extract the heart rate variability. And once we're able to extract the repetition in this two-dimensional matrix, then I'm now able to segment this fairly noisy time domain signal and be able to extract the individual heartbeat. So for example, I'm able to know that it's 797 milliseconds is the first heartbeat, then the second heartbeat is at 811, 828, and so on and so forth. And then I'm going to restart again in the second region and then again in the third region. And now that we're able to extract the heart rate variability with high accuracy, I can take them, I can combine them with the breathing and the movements, which we know that we can extract with the good accuracy. I can feed them into a actually fairly straight standard regression model or some neural network and be able to extract people's different stress levels. There's been a lot of work, as I mentioned, in the affective computer community to go from stress features to stress level. The main challenge really was in being able to extract the heartbeats in a motion robust way. So we evaluated this system with 22 subjects in different environments. We tested it with different activities, including we put it by someone's bed while they were sleeping, when they were reading, when they're speaking, when they're typing, when they're studying for their exams. Ignacio asked me this question earlier, that we've tested it up to 12 feet across people's different orientations. The ground truth, we obtained it from an on-body sensor for the HRV. But for stress levels, we used different task difficulties, which is basically you give people different tasks and you know that there is different levels of stress that or cognitive stress that they experience from different tasks. And we also used questionnaires that people needed to fill every 15 minutes about the level of stress that they were experiencing. So first, I want to show you the HRV, the heart rate variability extraction accuracy. The way I'm going to do this is I'm going to plot on the y-axis the accuracy, which is the same accuracy I was measuring before, and on the x-axis the median time between estimates. So ideally, I want to be able to capture estimates very frequently so that I can extract heartbeats. And remember that for RF-SCG, when the person was perfectly static, we got an accuracy of around 98.5%. Now, if the person is quasi-static, so for example, people who are sitting and watching a video, the accuracy drops a bit to around 85.9 or 90%, but it remains relatively high. And with WiStress, the accuracy when someone's quasi-static is a little bit higher. It's around 90 to 95%, which is just because it's more robust to even small movements that someone does while they're conducting their daily activities. Now, what I want to do is I want to move from people who are static or quasi-static to what happens when people are moving. So the whole region that I was describing before was here when the person was quasi-static. Now, let me show you what happens to RF-SCG when the person is moving. As you can see, the accuracy for RF-SCG, this shows the standard deviation in accuracy and the standard deviation in time between estimates. The accuracy drops to around 60%, which is pretty low if we want in extracting the heartbeat, the heart rate variability. But because WiStress has a robust mechanism of being able to being robust to movements, the accuracy of WiStress jumps to around 90%. So the main benefit here of WiStress over RF-SCG is that it is able to capture the individual heartbeats in a way that is robust to people's movements without telling people, oh, you need to sit here phase the device in this specific way. People come in and go, like I go out of my office, I come back in, I get around with my daily activities, and it is able to monitor my individual heartbeats with pretty good accuracy. I want to show you one last result, which is about the impact of different features on accuracy. Remember that I said the heartbeat alone is an important feature, but also other features are important. And I want to show you on the y-axis the accuracy in being able to classify between stress levels. We showed both 2-class between high level and low level, and 3-class classification, high, medium, and low. And if you have the heartbeats alone, or the heart rate variability alone, then you get an accuracy of 70 to 80%, whether it's 2-class or 3-class. But then each of the motion and breathing allow us to increase our accuracy. And when we combine all of these features together, then you get an accuracy of around above 80 or even above 90%, depending on whether it's 2-class or 3-class, in being able to identify people's stress level. And so the main take-home message here is that because we're able to extract the heart rate variability in a motion robust way, not only can we now enable better cardiovascular monitoring and be able to extract the seismocardiogram with higher accuracy, but we're also able to infer people's stress levels in a non-contact manner. And that paves the way for us being able to have interventions where you can tell people to take actions that would reduce their stress level so that it does not lead further down the road to cardiovascular diseases. And so in this talk so far, I've told you about our work on wireless, using wireless reflection to enable long-term non-contact cardiovascular monitoring. Over the next few minutes, I want to shift gears a little bit and just tell you about some of our work on sensing the human body, not from the outside, but from the inside, and how this also has applications to some emerging applications in machine learning. And as I mentioned, this different thrust focuses on being able to sense the human body from the outside. And we actually started it when a few years ago we were watching the World Mobile Conference. I don't know if any of you have seen it, and a man received a micro implant under their skin live at the World Mobile Conference. Ignacio, do you wanted to say something?
No, I feel like this is home, so I know the place. I've been in this conference, yes.
The only thing that you could do with this implant is you could identify a person. So for those of you who are familiar, it's like an RFID right under the skin. And it could only be implanted at superficial depth. In fact, in a recent op-ed article, another person wrote that someone who received a microimplant wrote, my implant is both less scary and less useful than you might think. Now, while implants right under the skin are not very useful, if you can take them and put them deep inside the human body, then they have many applications in digital medicine. And so over the past few years, we've setting out to build microimplants like this one, which have no batteries, and put them inside the human body, and we wanted to be able to communicate with them from outside the body so that they can send information. So, and our approach for powering them up and communicating with them when they don't have batteries is to use wireless power. So we use a wireless device outside the body, transmits the signal, goes through the body, the sensors harvest energy from it, power up, and then they communicate their data in order for us to sense the person from the inside. And this has so many applications in digital medicine. So for example, one application is in long-term drug delivery systems. So today, when you take a medication, you envision that it immediately releases the drug inside the body. Or, for example, there's been interest in these smart pills that have large batteries. But if you can eliminate the battery altogether, then you can enable long-term drug release inside the body. Or if someone forgets to take their medication, with these types of microimplants, you can trigger the drug release. You can also envision a network of microimplants that sit inside the person's body in order to monitor their body from the inside. Oops. So for example, you can monitor a person's glucose or stomach condition, or maybe in the future, and for future pandemics, we take a sensor that sits inside our body, and if we are exposed to COVID, then it automatically alerts us and tells us to self-isolate. And there's also many other applications for wireless and batteryless microimplants. For example, artificial pancreas for diabetes patients, deep brain stimulation for patients with, for example, Parkinson's or epilepsy. But the problem, but we're not there. And the reason is today's microimplants are primarily limited to right under the skin, and their capabilities are very limited. So over the past few years, we've been, as I mentioned, on a mission to develop technologies that can remotely be powered up, and we can communicate with deep tissue, batteryless, and intelligent microimplants. Now, while I don't have time to go into details into this, I would just want to show you one of the implants that we built. So for example, here, you can see that the implant has a microchip. We also built it on an antenna that reprogrammed itself. It's on a flexible substrate. And so what that means is it can be rolled into a pill form. For example, if someone wants to swallow it, or because it's flexible, it can be laminated on an organ. And we built this IC in collaboration with Professor Ananta Chandrakasan in EE. And this IC actually has many different capabilities. It can be powered up, it can communicate, it can do onboard sensing, and so on. And so first, what we showed is that this led to the first successful demonstration of wireless power and communication with a deep tissue batteryless microimplant inside the living animal. And this was in collaboration with medical doctors at Brigham and Women's Hospital and Harvard Medical School. And we started with power because being able to power and communicate is the first step to being able to enable any type of application. First, you need to deliver power and give it energy. And then on top of it, we started pushing down the power consumption. So we pushed it down to 350 nanowatts, pushing up the throughput to 6 megabits per second, and allowing it to to adapt to surrounding tissues. And most recently, what we've added, now that you're able to extract sensor data from the human body, we started adding security on top of it, because of course you don't want someone to be able to hack into a sensor that is inside your body, and you also want to ensure the confidentiality of the data that you're sending outside. And we started adding also sensing capabilities. So in our upcoming work, we're showing that you're able to do gastric motility monitoring by measuring using PZT-based strain sensing of, for example, stomach conditions. And looking ahead, we're building on this ability of doing microimplants to go beyond. So we're doing monitoring. We want to be able to do long-term monitoring and also moving from monitoring to stimulation. One of the reasons that I wanted to share this is I think one of the very exciting applications here is how do you go beyond powering, communication, sensing to being able to do in-body machine learning and in-body inference. And this ties into some of our other work where we've been working on batteryless machine learning sensors for climate monitoring. But there's a lot of applications for health monitoring if you want to do onboard inference or edge inference, or split the type of inference that you're doing between the edge and between a more powerful sensor. And so with this, I've told you about our work on wireless and batteryless microimplants. I've given you a glimpse into it. I've also shared with you our research on wireless reflections to enable long-term non-contact cardiovascular monitoring. Now, of course, none of this work would have been possible without my amazing students and researchers and our collaborators who you see here. Each of us, we like to build things. Sometimes I say we're like we're the blue collars of academia. So we really like to build things with our hands. And so you see them carrying some of the sensors. You see over here, my postdoc Ansu, who led a lot of the work that we've been doing on contactless monitoring, holding the TI chip. And we work together to enable some of these wireless and batteryless sensing applications for health applications and for climate monitoring and for emerging domains. And with this, I will wrap up my talk. Thank you very much for listening. I'm happy to take any questions. And also the QR code is if you want to see any of our websites, papers, or videos, they will lead you to them. Thank you.
Thank you so much, Fadel. And I'm already trying to open your QR code. Yeah, that was great. And I have some questions, but maybe we can let our audience today to ask any question, because now we have limited time. So I don't want to take. Let's see, David, please. We have a question from David Sontag.
Hi, can you guys hear me?
Yes.
Yes.
Thank you, Fadel. It's always super fascinating to see your work. I was curious whether, I do a lot of, I and many others faculty here are work a little bit more on the clinical side in terms of, how would you use existing clinical data, both to help research and to help patients. And I was curious whether, what some of the obstacles you might have seen were in terms of closing the loop between what you can observe from the patient perspective and phenotypes that you might want to predict downstream, which might only be recorded in clinical data.
Yeah, that is a great question. And frankly, I'm not sure. But maybe I'd be curious to hear your thoughts actually on this question. What can you, because what we're trying to do is to get new types of data. Of course, you want to get the data that is that complements, like the type of data that complements what is already available. And maybe you want to also go back in time and see if you can correlate these. Recently, we've been looking. I will add that some of this research was actually done during COVID, and a lot of this actually was done during that. And it was quite hard to do experiments with unhealthy subjects. And the reason why it was hard is because people who have cardiovascular diseases are the most prone to complications. But we've been recently working on also recruiting people who have different types of cardiovascular diseases and try to correlate it with their medical history, or even be able to do long-term studies. And I'd be curious to also reverse this also question to you and hear what your thoughts would be on how would you try to combine this data?
I mean, one long-standing challenge in many fields, including in oncology, is how to get a better picture of what's going on with patients while they're at home. That may give you better insight into treatment effectiveness, complications of treatment, and so on. Now, some of the signals that you're observing conceivably could provide a lens into that. Of course, that also relates to work that Dina does and you've done with Dina as well. And so, that would be one place. But I think even in the cardiology example that you gave, that question of how do you correlate with patient's past medical history is itself a challenging question if you don't have access to that past medical history.
That is true. Yeah. That's a very interesting question. I think trying to transition these two and test them with, like the way this works, the way this research has evolved over the past few years is first, can we extract something new that we didn't think that was possible? 2, can we now make it robust? And 3, how do we now tie it to like clinical, something that is clinically meaningful? And so we did that with motion, with like mobility patterns. I think the cardiovascular angle is very exciting because it's also very different, but it also comes with its own set of new challenges.
Yeah, and I guess for that, I would suggest, particularly for an MIT audience, we have a very strong group of machine learning folks working on cardiology at the Broad Institute. And so they're called the ML4H group. And if you haven't already connected with them, I think giving a talk in their seminar, I can make an intro, would be a really great way to start to test that out.
Yeah, that'd be great. Yeah, thanks a lot, David.
And I was wondering, Fadel, did Devon Newman approach, to use some of this technology for the space missions, or like now that you're exploring out of space stuff?
So yeah, Deva, I mean, we've had discussions, of course, with Deva on this. We're thinking about what we want to send to space. I think that's and where we want to send to space. There's a mission to the moon. So it might either be part of that, but maybe even beyond that in deeper space.
That's cool. I mean, we are above time now, so if there's no other question, maybe we can leave it here. And for the benefit of the audience today, if anyone wants to watch it again, we recorded this and it's going to be on the Jameel Clinic events. Again, Fadel, thank you so much. It was fantastic, and great job, all the team here. Thank you again.